Hello, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for your sleepy minds. Tonight we will follow a single element, iron, from the hearts of dying stars to the hidden heart of our own planet, tracing how it formed, how it traveled across space, and how it finally settled deep below your feet and inside your blood. So settle in, dim the lights, and get cozy. But before you do that, take a moment to like the video and subscribe to the channel. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world, and thank you so much for being here. Iron is ordinary to us. It holds up bridges, runs through train rails, and rides in your red blood cells as part of hemoglobin, carrying oxygen to every corner of your body. You find it in meteorites on farm fields and in the bright sparks of a grinder in a workshop. Because it is everywhere in human life, it is easy to forget the strangest truth about it. Iron is not from Earth. It could not have been made here in the way stars make it, and it was not forged in volcanoes or frozen in ice. The atoms of iron in your keys and in your blood were born in stars that lived and died long before the sun existed. To see why, we have to step back to the start. The Big Bang made a universe full mostly of hydrogen and helium with a trace of lithium. That was the simple recipe. Everything heavier, carbon in trees, oxygen in air, calcium in bone, and iron in rock, came later, cooked inside stars. Stars shine because they fuse small nuclei into larger ones, releasing energy early in a star's life. Hydrogen fuses into helium. In heavier and older stars, helium fuses into carbon and oxygen. With rising pressure and heat, fusion builds still heavier elements: neon, magnesium, silicon, sulfur. This ladder of fusion works because each step gives off energy, and that energy pushes back against gravity and keeps the star stable. But there is a wall in this ladder, and iron sits on that wall like a locked door. When a star tries to fuse elements into iron and beyond, the math flips. Instead of giving off energy, the reaction would demand energy. There is no gain left to hold the star up. Iron, especially the iron group nuclei, near iron 56, marks the point where exothermic fusion stops. That is why we say iron is the end of the line for normal stellar burning. In the core of a massive star near the end of its life, the pathways of silicon burning assemble nuclei that quickly decay into nickel 56, then cobalt 56, then iron 56. The core fills with these iron group nuclei that cannot give the star more support. Gravity, which had been balanced for millions of years, finally wins. The core collapses in a heartbeat. Temperatures and densities leap to extremes. In that brief, violent moment, the core collapse supernova, shockwaves and a flood of ghostly particles called neutrinos rush outward as some of the iron group nuclei are thrown into space. Heavier elements are also formed in the chaos by rapid captures of neutrons. In another class of explosions, type Ia supernovas, a dead white dwarf star is pushed over a limit and carbon and oxygen ignite all at once. The star is blown apart, and for a short while it becomes a factory for iron group elements, again flooding space with nickel that decays to iron. Across the galaxy, over billions of years, these blasts spray iron into the thin gas between stars' dust grains form. Iron sticks to them or hides in tiny minerals. New clouds collapse, new stars light, and around some of those stars, disks of rock and ice and gas start to swirl. The raw material of planets our Sun formed from one of those enriched clouds about 4.6 billion years ago. The disk around it held the leftovers of many past stars, broken and mixed. Carbon from one, oxygen, and silicon from another, iron from several. In the inner region near the newborn sun, where it was hot, metals and rock could survive, but ices could not. So the small rocky worlds, Mercury, Venus, Earth, Mars, grew from those solid grains by countless gentle collisions. Iron was plentiful in that mix, because the galaxy had been seeded by ages of explosions. The young Earth started as a jumble of rock and metal. As it grew and warmed from impacts, from the decay of radioactive elements, and from the squeeze of gravity, the heavy stuff, like iron and nickel, softened and began to sink. The lighter stuff, like silicates rich in oxygen and silicon, floated upward. In time, Earth sorted itself into layers, a metal-rich core below, a rocky mantle above, and a thin crust on top. That is why iron today is mostly hidden. It is down there, more than half of Earth's mass, turning slowly and helping drive the magnetic field that shields you from solar wind. A small fraction stayed in the mantle and crust, locked in minerals, rising in ores, slipping into your diet. But its story is older than any mountains. Each atom of iron had a life before Earth, in fires far hotter than any furnace. That is what we will unpack, step by step, how those dying stars built iron, how supernovas threw it outward, how the solar system trapped it, and how this element became both the heart of our planet and the quiet worker in your blood. To understand why the iron in your keys and your blood is older than the sun, start at the very beginning and move forward in slow steps. Right after the Big Bang, the universe was a blinding, expanding fireball that cooled as it spread out. In the first few minutes, when it was still hot and dense enough for atomic cores to bump and fuse, only the lightest elements could form in any real amount. That short window made lots of hydrogen, a hefty share of helium, and a tiny trace of lithium. Then the universe got too thin and too cool for more fusing. No carbon, no oxygen, no silicon, no iron. For those you need long-lived furnaces under crushing weight, and that means stars. Gravity gathered the first gas clouds, mostly hydrogen with helium mixed in, and squeezed them until their centers heated and lit. Inside those first stars, and all the generations that followed, a simple rule drives the show. Fusion works when you push small atomic cores together, and the result gives off energy. That released energy pushes back on gravity and keeps the star from caving in. Early on, hydrogen fuses into helium. In larger, older stars that have burned through their hydrogen, helium can fuse into carbon and oxygen. With higher temperatures and pressures, the star can ladder up to neon, magnesium, silicon, and sulfur. You can picture the core adding layers like an onion. Hydrogen burning outside, helium burning farther in, then shells where heavier fuels are used closer to the center. Each step only works if it pays out energy. There is a natural stopping point set by the way nuclear matter is glued together. If you graphed how tightly different nuclei are bound, you would see a broad hill that rises from hydrogen up to iron and its neighbors. Climb the hill toward iron, and fusing releases energy. Try to go past the top, and the math flips. Fusing heavier than iron does not pay you back. It costs you more than you put in. A star cannot support itself by running an energy-losing reaction at its core. That is why iron is a wall for normal stellar burning. In the final days of a very massive star, the silicon burning stage piles up nickel-56 in the center, which quickly decays to cobalt-56, and then to iron-56. Those iron group nuclei sit like ash from a finished fire. They cannot be burned to hold up the star. Gravity, which has been pushing all along, finally runs out of opposition. The core collapses in a fraction of a second. The outer layers crash inward, hit the rebounding core, and a shock wave rips outward. Neutrinos made in the crush stream through, and deposit a bit of energy on their way, helping the shock race on. In that blast, the star throws its iron outward, along with layers rich in other elements. In a different path to a similar end, a dead white dwarf in a close pair of stars can steal matter until it reaches a critical mass and ignites carbon and oxygen all at once. That runaway turns the whole star into a bright bomb that manufactures a huge load of nickel-56 that decays into iron and sprays it across space. These explosions are rare on human timescales, but common on galactic timescales. Over hundreds of millions of years, they salt the thin gas between stars with iron, and the rest of the periodic table, dust grains grow in that gas, some of them with iron inside, and gravity gathers those enriched clouds into new star systems. Our solar system formed from one such cloud, the newborn sun lit in the middle, and a flat disk of leftovers spun around it. Close to the sun, it was too hot for ices to last, but rock and metal could survive, so tiny iron-bearing grains stuck together in slow collisions to make pebbles, then boulders, then moon-sized bodies. Those bodies smashed and merged until a young Earth stood there, hot from impacts and from the decay of short-lived radioactive isotopes. In that heat, the heavy stuff softened and sank while the light stuff floated, and Earth sorted itself. An iron-nickel core deep inside, a rocky mantle above, and a thin crust at the top. That is where your iron lives today, split between the hidden heart that drives Earth's magnetic field and the scattered ores that miners find in ancient rocks. None of that iron was made by volcanoes or earthquakes. Earth's engines move atoms around and change minerals, but they do not build new nuclei. Only stellar furnaces and stellar deaths can do that. So when you hold a cast iron pan, or read about iron in meteorites, or talk about iron in your diet, you are handling material forged under pressures and temperatures no planet can reach, in events your eyes will never see. The reason it feels ordinary is that the universe did this work long before you were here. The reason it is everywhere on Earth is that stars did it so often that by the time our system was born, the local raw materials were already rich in it. Earth did the sorting and gathering. The cosmos did the making. Picture the last flash of a dying star fading and its broken layers racing outward into space. Inside that expanding cloud, temperatures fall from tens of millions of degrees to the point where atoms can exist, and among the first stable survivors are the iron group nuclei. The blast has made or exposed. At first they are just fast, naked atomic cores, but as the remnant cools, they grab electrons and become actual iron atoms. The cloud keeps widening for thousands of years, thinning into what astronomers call the interstellar medium, basically the galaxy's very thin air. Out there, iron does not float forever alone. It runs into other atoms and tiny clusters, sticking when collisions are gentle, bouncing when they are not. Some iron ends up locked inside microscopic silicate grains, rocky glass made of silicon and oxygen. Some condenses as specks of metallic iron. Some binds into tiny oxides. Magnetic fields thread the gas. Shockwaves from other stellar blasts roll through, and each push and tug mixes the cloud farther. So whatever iron came from one star is soon stirred together with ash. From many over millions of years, those thin, cold regions of gas and dust settle into darker, denser patches called molecular clouds. Molecular, here, just means a place cool and sheltered enough that atoms combine into molecules instead of being knocked apart by radiation. Inside those clouds, iron-bearing grains pick up thin frostings of ice, water, carbon dioxide, simple organics. And the grains drift, collide, and clump like slow snow. Gravity is patient. Where enough material gathers, a lump starts to collapse, and in the middle of that collapse, a new star will light. Around it forms a wide, flat disk of leftovers, rock dust, metal flecks, and ice swirling like a record. This is the birthplace of planets, and it is where iron's journey becomes personal for us. Close to the hot young sun in that disk, water ice and many ices cannot last. They vaporize. But metals and rocky grains tolerate the heat. At this distance, iron is one of the most stubborn solids in the mix, and because it is heavy and sticks well, it helps seeds grow. When two grains meet, sometimes they rebound. Sometimes static forces make them cling. Sometimes they weld a little at the point of contact. Billions of those gentle meetings are enough to turn dust into pebbles, pebbles into boulders, and boulders into city-sized bodies called planetesimals. Some of those early bodies get big enough and hot enough inside from radioactive decay and from constant impacts that their iron melts and trickles inward. That simple act, heavy liquid metal sinking, lighter rock rising, is differentiation, the same sorting that later happened in Earth. When later collisions smash such a differentiated body to pieces, the fragments spray the disk with two distinct kinds of meteorites: stony pieces from the rocky outer layers and iron-nickel pieces from the little core. The iron meteorites, farm kids still find on the prairie, are survivors of that early violence, natural steel from the hearts of failed worlds. You can see their story etched inside them. Cut and polish one, and you reveal crisscross patterns called Widmanstätten lines, which grow only when an iron-nickel alloy cools painfully slowly inside a parent body. Cooling that can take millions of years, before being shattered and thrown free. While that drama plays out, Earth is gathering mass from the same disk. Every impact brings more iron. Some arrives as tiny metallic grains mixed with rock, some as full iron meteorites that plunge through the air and splash into the young planet's surface. As Earth grows, the interior warms and softens. Iron and nickel begin their deep drift toward the center, while a fraction of iron stays behind, trapped in minerals in the mantle and crust. A share of undeveloped dust, still just millimeter-sized, is swept harmlessly into space or fed to the sun. Another share is stored in the asteroid belt to fall much later as shooting stars and rare falls. So the iron in a bridge girder, a cooking pan, or your hemoglobin did not travel in a straight line. It was cooked in one or more stars, hurled outward in blasts, cooled into atoms, trapped in grains, shuffled for ages in cold clouds, spun into the newborn solar system, knocked into clumps, melted and sorted, sometimes shattered, sometimes swallowed, and finally folded into a planet that kept the bulk of it hidden in a core while letting a thin rind ride up to the surface for creatures like us to mine and eat. When you pick up a small iron meteorite at a museum and feel its surprising weight, you are holding a page from the middle of that story. Not the first page, that was starlight. Not the last page, that is Earth's core. But a page where iron has already been through fire, vacuum, ice, collisions, and time, and somehow stayed itself. When the young Earth was still a violent construction site, the surface was a rolling ocean of lava and broken crust, and inside that heat, the heavy stuff began to move in a way that changed the planet forever. The metallic part, rich in iron with some nickel mixed in, melted first and trickled downward like dark rain through a glowing rock storm toward the center, while the lighter rocky part, made mostly of oxygen and silicon with other light elements, floated upward and cooled into the mantle and the first crust. This slow sorting is called differentiation, but you do not need the word to see the picture, because it is the same reason the oil in a salad dressing floats above the vinegar. Only now the oil is molten metal, and the vinegar is molten rock, and gravity is far stronger. Once enough metal reached the center, it pooled into a growing core, and as more metal arrived, it squeezed and heated the core even more, so the planet set up the layered structure we still live with today. A solid inner core wrapped in a liquid outer core, both made mostly of iron, then the thick rocky mantle, then the thin crust where oceans and continents sit. This is not guesswork from a textbook. We can test it, because when big earthquakes strike, they send different kinds of waves through Earth, and those waves bend, speed up, slow down, or stop depending on what they pass through. And by timing them as they arrive at instruments around the world, we can draw a picture of the deep interior the way a doctor uses sound to see a baby. So we see that some waves cannot pass through liquid, and they cast a shadow that proves there is a liquid layer inside. And other waves change speed in a way that reveals a solid center inside that liquid, a core within a core. The whole planet also spins like a top with a certain moment of inertia, which is a fancy way of saying how mass is spread out, and Earth's spin tells us mass is concentrated toward the middle more than it would be if the inside were just rock, so the math demands a heavy heart. We even know the core cannot be pure iron because its density is a bit too low. So there must be lighter ingredients dissolved in it like sulfur, oxygen, or silicon. The same elements that traveled with iron in the disk that built the planet and that blend changes how the core melts and flows. The flow is the key to the next act in the story, because the outer core is not still. It is a deep metal ocean moving in slow loops, churned by heat from below and by the planet's spin, and moving metal carries electric charge, which makes magnetic fields, and those fields feed back on the flow, building a self-sustaining engine called a dynamo that turns the core into a giant slow magnet, and that magnet reaches far into space as the magnetic field that a compass feels. This field is not decoration. It is a shield that deflects much of the charged wind blowing from the sun, guiding it around the planet and letting only a fraction leak down near the poles, where it lights the sky as auroras. Without that protection, the upper air would be stripped more quickly by the solar wind, and over long time the planet could lose water and air the way smaller worlds do, which is why iron's journey from dead stars into our core is part of the reason your lungs have air to breathe right now. We see the field change and wobble, and sometimes flip over geologic time in records kept by lava that cooled at the surface, because iron-rich minerals in those lavas act like tiny compass needles that freeze in place as the rock cools, pointing the direction the field had at that moment. So old flows are a diary of a living core. We also hold samples in our hands that hint at what the core is like, because when ancient small worlds were broken in the early solar system, their metal centers were torn open and pieces fell toward young Earth, and some survived as iron meteorites that you can cut and polish to reveal beautiful crisscross patterns that only grow when an iron and nickel alloy cools very slowly inside a big body, patterns that whisper the cooling history of a core not unlike our own. Put all of this together and the picture is clear in plain language, even without equations. Earth's iron did not start here. It was forged in older suns, scattered by explosions, gathered into our planet, then sank to the middle to power a hidden engine that runs our magnetic shield, while a thin leftover share stayed in rocks for people and microbes to use. So the simple act of picking up a magnet or watching curtains of green light wave over a polar sky is a small connection to that deep, unseen heart of iron that came from far away and now holds our world together. Most of Earth's iron sank inward during the planet's hot youth, but a thin share stayed mixed through the mantle and crust, and over time that share was shuffled upward by slow rock recycling until it reached places where people could find it. The story is calm and simple when you say it slowly. Deep rock melts here and there, either where plates pull apart or where one plate dives under another. Melts are like soups. Some ingredients prefer the liquid, some prefer crystals. Iron can follow both paths. Sometimes it stays in dark, heavy minerals inside cooling magma and later shows up as dense, iron-rich layers in ancient intrusions. Sometimes hot water moves through the cooling rock and drags iron along, then drops it again when the water cools or reacts with other rocks. Those are hydrothermal veins in plain terms, hot, mineral-laden water drawing lines through stone. But the single biggest stage for iron at the surface was the ocean of deep time. Early Earth seas were poor in oxygen. In such water, iron in the dissolved state stays mobile. Geologists call that form ferrous iron and write it as Fe2+, but the only thing you need to remember is it dissolves. Then tiny life began to change the surface chemistry. Microbes learned to use sunlight and release oxygen as a waste product. At first, that oxygen had plenty of work to do, reacting with things in water and rock. When oxygen met dissolved iron, the reaction changed the iron into a form that does not dissolve easily. That form, ferric iron, written Fe3+, falls out as rust-colored flakes and gels over vast spans of time. This simple switch from dissolves to falls built the layered rock called banded iron formation. If you have ever seen a polished slab of it, you have seen thin red and grey stripes repeating for meters. The grey layers came from silica-rich muds or iron minerals laid down without much oxygen. The red layers came from periods when oxygen spiked and iron rained out as oxide. Think of it as the planet's slow breath recorded in stone. Low oxygen, high oxygen, low again, on and on. These deposits are old, mostly older than 2 billion years, and they supply a huge share of the iron the modern world uses. After the seas and air held more steady oxygen, iron at the surface kept reacting with water and air to make oxides and hydroxides. In warm, wet climates where rock breaks down, that process can strip away lighter elements and leave iron behind as earthy, iron-rich soils and crusts. Miners call those laterites if you want the word. The idea is just weathering concentrates what does not wash away. There are other routes too. In some ancient, slowly cooling magmas, iron formed dense oxides like magnetite and ilmenite that settled like snow to the bottom of the magma chamber, and later became thick, mineable layers. In volcanic seas, hot springs on the ocean floor vented iron that reacted and settled around the vents. Each of these settings is simple if you keep the picture big. Iron moves with melt or water, meets oxygen, and stops moving. Once it stops, time builds volume. All of that happened long before smelters and blast furnaces. For most of human history, people did not know how to win iron from rock copper, and tin came first because their ores melt and separate more easily. The earliest iron tools in many places were made from meteoritic iron, natural metal that fell from the sky already smelted by the vacuum of space and the slow cooling of parent bodies. Later, humans learned to coax iron out of bog ore and red soils with charcoal fires and airflow, layer by layer, until a spongy bloom of metal could be hammered into shape. Modern furnaces just repeat the same chemistry with better heat. Carbon removes oxygen from iron oxide and releases it as carbon monoxide and carbon dioxide, leaving liquid iron behind. None of this creates new iron. It only moves and cleans the old iron put here by stars. You can see that truth written across whole landscapes. The red beds of dry country, colored by iron oxides, are the planet's rust caught in place. The red line in many old cliffs marks a time when groundwater brought oxygen through sand and stained it. Mars looks red for the same reason. Iron at the surface met oxygen and turned to dusts of hematite and related oxides. On Earth, the process is bound up with life. Microbes eat iron for energy, both by giving electrons to it and by taking electrons from it, shuttling it between the dissolved state and the solid state like tiny miners working day and night. Plants take iron in to run enzymes. Animals borrow it for blood. Rivers carry a little to the sea, where it feeds plankton in the right amounts, but chokes life when the balance tips. The cycle is slow but sure. Weather loosens iron from rock. Oxygen locks it into solids. Burial turns those solids into ore. People dig the ore, take the oxygen off, and turn the metal into bridges and rails and tools. Then water and air start the rust again. Under each step is the same quiet fact. Every atom of iron involved in this loop was born far away, thrown out by events more violent than any storm, sprinkled into the gas that later built our sun and planets, and finally lifted to the light by chemistry, water, and time. If you want a piece of evidence you can hold in your hand that iron didn't start on Earth, go to a museum case of meteorites and look at the ones that look like weathered steel. Those are iron meteorites, natural iron-nickel metal that once sat in the cores of small, early worlds that melted and sorted just like Earth later did. When those little worlds were smashed apart in the young solar system, pieces of their metal centers wandered for ages, and some fell here. Cut and polish one, and an astonishing crosshatch appears, a frosty silver pattern of long interlocking bands called Widmanstätten. Figures you get that pattern only when an iron-nickel alloy cools painfully slowly over millions of years inside a parent body, letting two metal phases, one a little poorer in nickel, one a little richer, grow side by side like crystals in a rock. No forge, no volcano, no modern factory produces that in bulk by accident. It is a timestamp from space. The chemistry tells the same story. Terrestrial iron in tools and rocks is almost pure iron with traces from smelting or from the original ore. Meteoritic iron is different. It almost always carries a lot of nickel. 5 to 20% is common, and a little cobalt in ratios that match other meteorites. If you test a suspicious old iron blade and it has that high nickel and cobalt in the right balance, you are likely holding sky iron. That is how we know, for example, that Tutankhamun's dagger blade was hammered from meteoritic iron. The ratios match, and the timing fits the era before smelting was widespread. The Inuit of Greenland did the same with the Cape York meteorites, quarrying tough iron straight from a fallen mass to make harpoon tips long before furnaces arrived. There are stony iron meteorites too, like palasites, where green crystals of olivine are set in a metallic iron-nickel web, a literal picture of the boundary between rock and metal in a small body. Slice one and hold it to the light. You are looking through a window into the structure of a failed world's interior. Even the plain rocks of space, the stony chondrites that make up most falls, carry iron in two ways, as tiny specks of metal and as iron bound in minerals. Their overall mix of elements matches the sun's non-gassy elements, which is a way of saying this is what the solar system started with before planets sorted themselves. Earth, by contrast, is missing many elements that love iron. Geochemists call them siderophile elements, from its crust and mantle, because those elements followed iron downward during core formation. Yet we still find small, even, solar system-like amounts of those elements in the upper mantle and in much younger rocks. That mismatch is a clue nicknamed the late veneer. After Earth's core had already formed and stolen most of the iron-loving elements, a final drizzle of meteorites and small bodies coated the planet with a thin layer of chondritic material, replenishing platinum, iridium, and friends near the surface. A single thin clay layer at the time of the dinosaur-killing impact is overloaded with iridium compared to normal crust. That spike is classic from space chemistry, and it rides in on iron-bearing rock. Even tiny isotopes keep the record. While a meteoroid is drifting between planets, cosmic rays, high-energy particles from space, smack into it, and make short-lived isotopes that decay like little timers. When we find a meteorite, those isotopes and their daughter products let us read how long it wandered in space, how deep it was buried in its parent, and roughly when it was knocked free. All of that chronology, chemistry, and texture converges on the same story. Metals fused and separated in small bodies. Those bodies broke and the shards fell. Bring that evidence back to Earth's big picture and it clicks into place. Our planet's surface iron is mostly locked in oxides and silicates because oxygen is common up here and iron loves to rust. The bulk of the metal long ago took the express elevator downward and now churns in the core. So where does the bright, nearly pure iron in a museum come from? From space, already smelted by nature's slow furnace and slow cooling. Where do the high nickel clues in ancient knives come from? From space, hammered into tools before kilns could free iron from ore. Why do we find specific iron-loving elements in crust and mantle at levels too rich to have survived core formation? Because of space again. A late sprinkle of chondritic debris that refreshed the surface mix. Even the red dust on Mars and the red beds on Earth point back to the same simple loop. Stars made iron, planets sorted it, weather and water moved it, and impacts kept adding it. Hold a meteorite and you hold a chapter of that loop. Strike it with a magnet and feel the tug. That pull is more than a neat trick. It is a handshake from a world that never finished becoming a world, and from the stars that fed it. Inside a massive star, the core runs an assembly line that climbs the nuclear ladder step by careful step. First turning hydrogen into helium, then helium into carbon and oxygen. Then with rising heat and crushing weight, it fuses neon, magnesium, silicon and sulfur, always choosing reactions that pay out energy, because that energy is the pressure that keeps gravity from crushing the star. And then the line reaches a hard stop called the iron wall. The reason is simple in spirit, even if the math is heavy. Nuclei are held together by a kind of nuclear glue, and there is a sweet spot where each particle inside a nucleus is as tightly held as it can be. That sweet spot sits around iron and its neighbours, especially iron 56 and nickel 56. When you fuse light elements up toward iron, you release energy, which is why stars shine for millions of years. Try to fuse past iron and the bill comes due. You would have to put in energy instead of getting it out, so the fusion engine stalls. In the last days of a very massive star, the core temperature climbs to billions of degrees, and a frantic stage called silicon burning begins, not because the star burns silicon like coal, but because chains of fast reactions rearrange silicon and other mid-weight nuclei into nickel 56, which then turns into cobalt 56, and finally iron 56 by radioactive decay. The tragic detail is how fast this all happens. Hydrogen burning can last tens of millions of years. Helium burning lasts millions. Carbon and neon burn for years to months. But silicon burning can run out in days. By then the core is a ball of iron group nuclei that cannot pay the star back with more pressure. Gravity wins. The core falls inward. The temperature spikes even higher. And another cruel process turns on called photodisintegration. Photons with extreme energy slam into iron nuclei and knock them apart, stealing heat to break big nuclei into smaller pieces. At the same time, the rising pressure squeezes electrons into protons to make neutrons, which removes electrons that had been helping to hold up the core. Everything that once propped the star open is gone in a blink. The core collapses until it hits densities found in atomic nuclei. It stiffens abruptly, and the infalling layers crash into this rebounding inner mass. A shockwave forms and tries to blow the star apart, but it stalls as it plows through the dense matter above. Then comes the strangest rescue in astrophysics. In the crush, the core spits out an ocean of neutrinos, ghostly particles that almost never interact with matter. Yet in this extreme pressure and thickness, even a small fraction of their flood deposits energy behind the stalled shock, which helps it surge again. When the shock breaks free, the star explodes. The blast hurls the iron-rich core ashes and the surrounding shells into space, and for weeks the light you see from a core collapse supernova is powered by the nickel to cobalt to iron decay chain glowing as it sheds energy. There is a second major route for iron too. In close binary systems, a dead white dwarf can steal gas from a partner star until it reaches a critical mass and ignites its carbon and oxygen in a runaway. The entire dwarf detonates, with no core left behind, and for a short time it manufactures a mountain of nickel-56 that later becomes iron-56. These type IR explosions are so bright and regular that we use them as yardsticks for the universe, and they are thought to be a prime source of the iron that builds up in galaxies over billions of years, because they keep happening long after the first wave of massive stars has died. Put these pieces together and the path looks clean. The binding energy curve sets a summit around iron, stellar burning climbs to that summit and stops, collapse and explosion throw iron into space, and the radioactive steps from nickel to cobalt to iron act like a light bulb timer that lets us watch it happen from across the cosmos. None of this needs fancy words to matter to you. The hemoglobin in your blood carries oxygen because iron can flip between two gentle charge states and grab or release O2, a trick baked into the nucleus and the way electrons sit around it. That nuclear identity was set when some star in our galactic neighborhood hit its iron wall long before our sun was born. The skillet on your stove, the bolt in a bridge, the slow compass needle that points north because iron atoms can line up tiny magnetic fields, the planet's core that churns a magnetic shield, all of it is downstream of a simple limit in nuclear bookkeeping. Stars can climb to iron by earning energy. They cannot climb higher without paying. They collapse. They explode. They seed the galaxy, and new systems like ours sweep up the harvest. The iron in your body and in your tools is not just old, it is the product of a universal rule that makes stars shine, makes some stars die, and makes the next generation of worlds possible. If you want the neatest proof that iron is not just common here but essential here, look at your breath and your blood and the quiet chemistry that links them, because the same nucleus hurled out of dying stars now sits in the middle of a ring-shaped molecule inside your red cells and flips gently between two states so you can live. Life chose iron, not for romance, but because, at Earth's surface conditions, iron can trade electrons easily. It can sit as Fe2+, a little reduced, or Fe3+, a little oxidized, and hop between those without tearing the whole molecule apart. And that small trick, made possible by the way electrons fill iron's shells, lets hemoglobin grab oxygen in your lungs and let it go in your tissues with only tiny changes in acidity and pressure. Step back and you see a pattern. The element that ended fusion in stars ended up as the element that carries air in animals. The choice shows up everywhere in biology once you know to look. In your muscles, myoglobin holds oxygen in reserve with an iron heme at its center, just like hemoglobins. And in your cells, little chains of electron handoffs that make ATP, the energy coin, are studded with iron in two main outfits: heme groups in cytochromes and tiny iron-sulfur clusters, cube-like bits where atoms of iron and sulfur share electrons. These clusters are ancient, probably adopted by early microbes when the oceans were rich in dissolved iron and short on oxygen, and they still sit at the heart of the machinery that runs you today, even photosynthesis, the light-harvesting engine that filled our air with oxygen in the first place, uses iron as a courier in its electron ladders. So iron helped write the planet's atmosphere, and now that atmosphere makes iron rust. The loop closes. Because iron flips charge so easily, it is food for microbes. Some iron eaters take electrons from ferrous iron and dump them on oxygen. Others pull electrons off organic matter and park them on ferric iron, turning rust back into dissolved iron. Whole dirt smells and colours come from this push-pull. Red beds where ferric iron settled in, grey streaks where microbes took oxygen from iron and made it mobile again, and wetlands where iron turns the water tea-brown as microbes work. The oceans feel iron's scarcity and plenty like weather. Over vast areas of the open sea, there is nitrogen and phosphorus for plankton to bloom, but growth stalls because there is barely any dissolved iron. It sticks to particles and sinks. So tiny spurts of wind-blown dust from continents, mineral shavings rich in iron, can kick off huge blooms that pull carbon dioxide from air, feed the food web, and then snow carbon into the deep. On long timescales, that dust-iron plankton dial is part of climate's subtle machinery. Another reminder that a handful of atoms, delivered or withheld, scales up to whole planet behavior. For an animal, the flip side of useful is dangerous. Free iron catalyzes reactions that make damaging oxygen radicals, so bodies lock it down. You carry iron in blood bound to transferrin, you store it inside a protein cage called ferritin that can pack thousands of iron atoms away like marbles in a safe, and you dole it out carefully to enzymes that need it. Too little and you get anemia. Tired, breathless, pale, because hemoglobin can't be built. Too much in the wrong place, and tissues corrode from the inside, which is why infections often feel like a tug of war over iron, with your immune system hiding it and microbes trying to steal it with special molecules. All of this everyday sleep-at-night physiology rests on a geologic light-years backstory. Stars seeded space with iron, disks of rock and metal formed. Earth's surface chemistry made iron scarce in air-rich water and abundant in old rocks. Life evolved in seas where iron's redox play was available, and once oxygen flooded the air, the planet wrote iron's history into stone as banded iron formations, while cells rewired to keep using iron safely in a harsher, rust-prone world. You can track that history in your own lab values and in a cliff face, and in a satellite photo of a dust plume seeding the South Atlantic. Same element, different scales, same rule. Iron is the perfect middleman for electrons at Earth's temperatures and pH, so the cosmos's favoured fusion endpoint became biology's favoured cofactor. That is the quiet thrill of it. There is star death in every breath, not as poetry, but as plain chemistry. A nucleus born where fusion fails now riding in a protein that loads your blood with oxygen on one side of your body and unloads it on the other, every minute, all night, while you sleep. If iron didn't start on Earth, we should be able to catch it in the act out in space. And the calm truth is we do, in multiple independent ways that all point to the same answer. The simplest is to read light like a barcode, because every element steals or sends out very specific colours when it's hot or when a bright lamp is behind it, and those thin, dark or bright lines in a spectrum are as unique as fingerprints. When we split the sun's light, we see an absolute forest of iron lines, thousands of tiny cuts across the rainbow that say, iron is here. And when we split the light from other stars, we can count how deep those lines are and estimate how much iron they contain, which is how astronomers talk about a star's metallicity, a simple shorthand meaning how much stuff heavier than hydrogen and helium this star has. And iron is the usual yardstick because its lines are plentiful and easy to measure. In exploding stars, the evidence gets louder, because the week-to-month glow after certain supernovas is powered by a tidy chain in which nickel made in the blast turns into cobalt and then into iron while releasing energy. And that decay acts like a slow light bulb that tells us iron is being made and thrown out. Point an X-ray telescope at the expanding wreckage of those blasts, and you see iron glowing in X-rays with a signature energy that matches iron's inner electrons being kicked and refilling. A flashing neon sign that says, "Iron in hot gas right here." And when we map those X-rays, we literally draw iron-rich knots and shells in the debris. Even quiet, long-lived galaxies tell on themselves, because the average iron content of their stars creeps up over cosmic time as many Type Ia supernovas, the kind that blow apart dead white dwarfs, keep seeding space with iron long after the first generation of massive stars has vanished. And that slow enrichment is measured by comparing iron lines to hydrogen lines in huge surveys and watching how the pattern changes with a galaxy's age. Now trade telescopes for shovels, and we still find space iron because Earth's crust carries thin timestamps made from a rare radioactive flavor of iron called iron-60, which has 2 extra neutrons and decays away over a few million years. So any we find near the surface must be fresh on geologic clocks, and yet deep-sea crusts, seafloor sediments, Antarctic snow, and even moon soil all contain faint layers of iron-60 that line up to a few million years ago. Exactly the age you'd expect if a nearby star or two died and dusted the solar system with a gentle drizzle of ejecta. That is not junkyard contamination. Its half-life is so short that it cannot be left over from when Earth formed, meaning we caught supernova ash on our planet's porch. We also detect iron riding in on today's interstellar dust stream, tiny grains that drift through the edge of the solar system and sometimes make it down here as micrometeorites. If you drag a magnet through gutter sand after a rain and look under a microscope, a surprising share of the little shiny spheres you pick up are melted cosmic dust rich in iron that burned and balled up as it hit the air. In space between stars, we see iron locked into dust by the way gas lines are missing. Iron compared with other elements, the iron is stuck in grains, not floating free. And inside our own atmosphere, we literally watch iron vapor trails from meteor showers with radars that see the thin layer of metal atoms left behind. Even the high-energy particles that rain down on detectors, cosmic rays, include a clear population of iron nuclei, heavy bullets that were stripped from matter in violent places and then fired across the galaxy by shockwaves, and their very presence tells us iron is common in the stuff being accelerated. Finally, the rocks that built our knowledge, the meteorites, carry iron in 3 voices at once, as nearly pure metal in iron meteorites, as iron-nickel beads sprinkled through stony meteorites, and as iron locked into minerals. Their overall mix of elements matches the solar system's starting recipe, and the metal portions are so rich in nickel and cobalt, with textures that only form by million-year cooling, that they can only be the cores and core edges of small worlds that formed and broke before Earth finished growing. Put the light, the X-rays, the radioactive crumbs, the dust, the cosmic rays, and the meteorites together, and you get one quiet, unavoidable conclusion in plain words. Iron is not a local quirk of our planet. It is a main ingredient of the galaxy, made in dying stars, visible in their light, drifting through space in dust, arriving here in grains and stones, and slowly building up the metal content of each new generation of stars. The key is that every method is different. Light, atoms, rocks, particles, and they all agree, which is what moves this whole story from nice idea to solid ground. Iron's most famous party trick on the surface has nothing to do with weight or rust. It's the way a small piece of it notices Earth's magnetic field and gently turns until it points north. And the reason that happens lies inside each atom in something as simple as spin. Electrons carry a tiny magnetic moment, like microscopic bar magnets. In most elements, those little magnets cancel because electrons pair up with partners pointing the opposite way, but iron keeps a few unpaired in a shell near the outside, and that gives each atom a faint preference for a direction. One atom by itself is too shy to matter, yet pack trillions of iron atoms into a crystal and a new pattern appears. Groups of neighboring atoms line up their tiny magnets together into patches called domains. Each domain is like a tiny region where all the arrows point mostly the same way. In a plain nail, those domains point in different directions, so the whole piece doesn't act like a magnet, the patchwork cancels out. Bring that nail near a strong magnet though, and the borders between domains slide. Patches that point along the magnet's field grow, patches that disagree shrink, and the nail briefly becomes a magnet itself. Take the magnet away and some of the domain walls drift back. The magnetism fades. That is why a fridge magnet holds a shopping list, but the list falls when you pull the magnet off. The steel door was only magnetized while the field was present. Make the iron a little different, add other elements, change the grain size, trap defects that pin domain walls like fence posts, and you get hard magnetic materials that remember the alignment even after the field is gone. That is how permanent magnets work. They are iron-based alloys engineered so those tiny domain walls get stuck and can't easily slide back. The opposite soft magnetic steels let the walls move freely. They don't stay magnetized, but they respond quickly. That is exactly what you want in transformer cores and electric motors, where a changing magnetic field has to tug domains back and forth millions of times a second without wasting energy as heat. Heat is the other lever on this story. Warm an iron bar and the jiggling of its atoms increases. The tiny magnets start to lose their shared direction. Pass a particular temperature, about 770 degrees Celsius for pure iron, and the material forgets how to support those lined up domains at all. That turning point is called the Curie temperature, and above it, iron is just paramagnetic. It is weakly attracted to a magnetic field, but won't hold magnetization. Cool it back down and the domains reappear. That flip matters in furnaces and for the planet as a whole. As lava at a volcano cools through its Curie point, iron-bearing grains inside lock in the direction of Earth's field at that moment, like tiny compass needles frozen in time. Millions of years of such rocks make a striped record on the seafloor that shows our planet's field has flipped north-south many times, and that the plates are creeping apart as new rock forms and moves away from ridges. The same iron remembers rule lets archaeologists date old hearths and kilns. When clay with iron minerals is fired, the grains reset. When it cools, they point at the field of that year. Read the directions, read the angles, and you get a magnetic timestamp. Zoom back to the workshop, and the story stays simple. The stainless knife that doesn't stick well to a magnet is still iron-rich, but its structure and added elements like chromium and nickel disrupt domain formation and motion, trading magnetism for rust resistance. Spring steels and tool steels harden because carbon and other atoms lock into the iron lattice, changing how domains move and how the metal bends and snaps back. Even the odd fact that iron changes crystal form with temperature, cubic in one way at room heat, cubic in a different way when hot enough, feeds the magnet story because the room temperature phase supports strong domains and the high temperature phase does not. All of that engineering rests on the same tiny cores, unpaired electron spins cooperating over long distances. And here is the satisfying tie back to the sky. Those unpaired spins exist because of how electrons fill the shells around an iron nucleus that was made in the last heartbeat of a dying star. The same nuclear identity that ends fusion in stellar cores sets the electron structure that lets domains form in your compass needle. So when you watch a compass settle, hear the low hum of a transformer, or see green curtains of aurora guided by Earth's field, you're watching crowds of iron atoms lining up their little arrows in chorus, then relaxing, then lining up again. A quiet choreography that links a street corner magnet to supernova ash and turns an element forged far away into a daily tool here at home. Iron wants company. Leave bare iron in air, and a thin film of water forms from humidity. In that film, oxygen steals a little charge from the metal and turns some surface iron into tiny loose flakes of iron oxide. Rust. It's slow fire because it is the same idea as burning. Oxygen combining with a fuel and releasing energy, only here it creeps instead of roars. Salt speeds it up by helping charges move through the water film, which is why seaside railings and winter road bridges suffer first. Once rust starts, it often traps more moisture and cracks paint, so fresh iron is exposed and the cycle repeats. We fight this in a few simple, clever ways. Paint and powder coatings work by blocking air and water. Keep the seal intact, and iron never meets oxygen, galvanizing dips steel in zinc, a metal that willingly sacrifices itself. If the coating is scratched, zinc gives up its charge first and protects the iron underneath. That's why ship hulls and street signs last stainless steel mixes in chromium so that a thin, hard chromium oxide forms on the surface and clings tightly. That clear, passive skin is self-healing in air, so the steel stays bright. On boats and pipelines, we bolt on sacrificial anodes, chunks of zinc or aluminum, so the ocean eats those blocks instead of the structure we care about of in simple design slows rust. Add drain holes so water can't pool, avoid tight crevices where damp air lingers, and use smooth finishes so dirt doesn't hold moisture. Nature plays both sides in the rust story. Some microbes breathe iron the way we breathe oxygen, pulling charge from dissolved iron and turning riverbeds orange. Others push charge onto rust and make iron soluble again, setting its cycle in motion underground. On land, the red skin of many deserts is iron oxide powder left behind after other parts of rock weather away. On Mars, the same chemistry painted nearly the whole planet. Iron met ancient water and oxygen and turned to dust that storms lift into the sky. Inside you, iron is handled with care because free iron can spark harmful reactions. You store it in a protein cage, ferritin, and ship it with transferrin so it cannot roam and rust tissues. The quiet link back to the stars is easy to hear now. Iron that was forged in violent light-years away events is, on Earth, a practical metal with one big weakness. It likes to relax into oxide when air and water touch it. Our paints, alloys, and sacrificial blocks are just ways to keep that ancient element in the form we need a little longer. Every bridge we protect, every skillet we season, every railing we galvanize is another small negotiation with a cosmic gift that would rather slide back to dust. Long before furnaces, people found small chunks of ready-made iron lying on the ground, meteorites, and hammered them into knives and points. It was rare and precious, sky iron, already metallic because it had cooled slowly inside a broken little world, rich in nickel so it was tough. Much later, humans learned to pull iron from earth rock. Early smelters heated iron-rich soils and ores with charcoal in a simple shaft called a bloomery. The hot carbon in the fire stole oxygen from the ore and left a spongy lump of soft, almost pure iron called wrought iron that blacksmiths could hammer and weld. Turn up the heat and add more carbon and the story changes. When enough carbon dissolves into iron, it melts at a lower temperature and you can cast it. That's cast iron, hard but brittle. The real breakthrough was learning to land between those two. Steel, iron with just enough carbon, and often other elements, to be strong, tough, and shapeable. Carbon hides between the iron atoms and locks the structure like wedges in a door. Cool slowly, and you get a mix of soft ferrite and hard cementite that shows up as fine stripes called pearlite under a microscope. Quench fast from red hot and the lattice traps carbon in a strained form called martensite. Very hard but also brittle. Temper, reheat gently, and that hardness relaxes into toughness. That heat treat dance, heat, quench, temper, is why spring and blades hold an edge. In the 1800s, the Bessemer and open hearth processes let us blow out extra carbon and control the recipe at scale. Then basic oxygen and electric arc furnaces made steelmaking cleaner and faster. Tiny sprinkles of other starborn elements tune the behavior. Chromium forms a thin, self-healing skin of chromium oxide for stainless steel. Nickel keeps steel tough in cold. Manganese cleans impurities and adds strength. Molybdenum and vanadium help at high temperatures and improve hardenability. How? Deeply heat treatment works. Grain size, tiny carbides, and trapped defects all steer how cracks start or stop. A microscopic city plan that decides whether a bridge cable survives storms or a tool snaps. Yet the base fact underneath never changed. No furnace on Earth makes iron atoms. We only rearrange and purify what dying stars handed us. Every beam in a building and rail under a train is a managed compromise between softness and hardness, between sliding domains and locked ones, between rusting away and resisting, all set by how carbon and friends sit inside an iron lattice born in supernova ash. When you pick up a stainless spoon, you're holding a quiet treaty between star chemistry and human craft, chromium guarding the surface, carbon strengthening the heart, iron carrying the load, cosmic metal tuned for breakfast. It's easy to say there's iron at the core, but the iron down there is not the same as the iron in a skillet. 2 million times atmospheric pressure and thousands of degrees change its behavior, its shape, even how sound moves through it. And we know this not by digging, we can't, but by recreating core conditions in the lab and reading earthquakes like CT scans. Start with the phases. The arrangements atoms prefer. At room conditions, iron can be body-centered cubic, ordinary structural steel, or face-centered cubic at red heat. But squeeze it hard and cool it, and the atoms pack into a tighter hexagonal pattern. That hexagonal form appears to match what the solid inner core prefers. Heat it further until it melts, and you have the liquid outer core, the metal ocean that convects and powers our magnetic field. What does hard squeeze, fierce heat actually mean? Pressures at the inner core are roughly 3 to 3.6 million times the air pressure at sea level. Temperatures are on the order of 5,000 to 6,000 degrees Celsius. To reach that in a lab, scientists trap a grain of iron between the tips of 2 flawless diamonds, a diamond anvil cell, then heat it with lasers while blasting it with X-rays from a synchrotron to watch how the atomic pattern changes. Others fire shockwaves through iron with high-speed impact or laser pulses and time how fast the waves run. The result is a melting curve and a map of which crystal forms survive where. Those maps, compared with the speeds of earthquake waves that cross the core, let us say in plain terms. The outer core must be liquid metal, the inner core must be solid metal, and the solid seems anisotropic. Sound travels a bit faster along one direction than another, which likely means the iron crystals are lined up by slow flow and growth. There's another puzzle. Pure iron would be too dense for the core we infer from gravity and seismic data. The fix is simple. Dissolve a little of some lighter elements into the iron. Candidates include sulfur, silicon, oxygen, hydrogen, maybe a pinch of carbon, all elements common in the early solar system, and happy to ride with metal. Mixing in light elements lowers the density and changes how the core melts and convects. As Earth cools, iron freezes at the center grain by grain. That inner core growth releases heat and squeezes out those lighter elements into the liquid above, making the outer core even more buoyant in places. Heat plus buoyancy drives rolling motion, the dynamo that keeps our magnetic field alive. The freezing front may not be smooth. Some studies hint at an inner core with a different crystal orientation, a kind of growth record written in metal. On the other end of the core boundary, where liquid metal meets solid rock, some scientists even argue for a slushy layer, a metallic mush that could damp seismic waves. None of these details change the big picture. Iron that stars made long ago now behaves like a different material under pressure, stacking more tightly, melting at extraordinary heat, and carrying a small cargo of lighter elements that tune its flow. We can't touch it, but we can watch earthquakes sprint and stumble through Earth and make the lab iron suffer under diamonds until it matches the way waves move below. When those match, we get confidence in a simple statement that ties the cosmos to the ground. Star-forged iron didn't just fall into Earth, it adapted to Earth's deep rules, and in doing so it built the metal engine that keeps our planet's shield and climate stable enough for us to sleep. Once you start looking for iron away from Earth, you see the same element telling different stories on every world. Mars wears iron on its sleeve. Its red deserts are dusts of iron oxide spread by wind and ancient water. And bits of magnetized rock there tell us it once had a working metal dynamo like ours, before the core cooled and the field faded. The moon is poorer in iron overall, yet its dark seas, the Mare basalts, are more iron-rich than the pale highlands. Bring a magnet near some lunar soil and a few grains will jump. Tiny beads of native metal made in micro-meteorite fire. Mercury is the extreme case. A small world with a giant metal heart, probably formed by violent sorting or stripping that left an iron-nickel core taking up most of the planet's radius. That outsized core still convects and runs a magnetic field. Out in the belt, you can meet worlds that never finished, from stony rubble to bodies that look like exposed core. The poster child is a metal-rich asteroid that we've sent a probe to, because if you want to study planetary guts without drilling Earth, a broken one is a gift. Iron also rides in on visitors. Some meteorites are nearly pure iron-nickel, others mix green olivine crystals in a metal web. A snapshot of the boundary between rock and core in small bodies. Cross the line to giant planets, and iron changes costume again. Deep inside Jupiter and Saturn, you won't find iron as bright metal, but as dissolved atoms inside crushing mixtures of hydrogen and ice, drifting downward as the pressure rises. Around some ultra-hot giant exoplanets, astronomers see vaporized neutral iron high in the dayside air. The night side is cooler, so models suggest iron could condense and fall. Iron rain is not a myth in these ovens. It's chemistry at 2,000 to 3,000 degrees doing what it must. Among rocky exoplanets, we found a few that seem too dense for their size, hinting at Mercury-like iron fractions, and others that are lighter, with more rock relative to metal. Those differences likely trace the same early violence we think shaped Mercury. Close in heat, impacts, and evaporation shuffling metal and stone. Even stars wear iron as a badge. We measure a star's metallicity using iron lines in its spectrum, and that number correlates with the odds of finding planets around it. More iron and other heavy elements in the birth cloud, more solid bits to glue into worlds. Everywhere you look, the pattern holds. Iron made in older stars gets recycled into new systems, then each planet's heat, size, and history tell that iron what role to play. Core, coat, dust, or vapor. On Earth, iron settled into a churning heart and a thin, rust-colored skin. On Mars, it paints the sky. On Mercury, it is the planet's story. On some faraway giants, it may fall as molten droplets through a black-orange twilight. It is the same nucleus in all places, but the same nucleus lives a different life under different rules. And every version, from desert dust to metal storms, is another reminder that the iron in your keys is part of a galactic circulation that never really stops. When lava cools or mud settles, grains of iron-bearing minerals inside behave like billions of microscopic compass needles, and the direction they settle or freeze in becomes a note in Earth's diary. Put enough notes together, and you can read motions of continents and flips of the magnetic poles across deep time. Here's the simple version. In fresh lava, magnetite and other iron-titanium oxides cool through a key temperature and lock in the direction of the magnetic field at that moment, thermoremanent magnetization. In lake or ocean mud, tiny magnetic grains align with the field as they fall and can be fixed in place as the sediment compacts, detrital remnants. Sometimes new iron minerals grow during chemical changes and inherit the field, chemical remnants. Each process traps a tiny arrow. One rock is noise. Thousands from many ages become a map. This is how seafloor spreading was proved. At mid-ocean ridges, lava oozes out, cools, and records the field. Because Earth's field has flipped north-south many times, the ocean crust preserves symmetrical barcodes of normal and reversed polarity on either side of the ridge toe, a magnetometer behind a ship, and you see stripes, dark, light, dark, marching away from the ridge like conveyor belts. Date a few patches with radioactive clocks, match the stripe sequence to the global flip record, and you can measure the rate the seafloor is moving in centimeters per year. The same trick works on continents. Basalts, baked contacts, ancient sediments, sample them across a region, correct for later tilts, and you get a paleomagnetic pole, the apparent position of the spin axis when that rock formed. Track those poles through time and they wander, not because the pole ran laps around the planet, but because continents slid to new latitudes and rotated combined different continents' paths, and the jigsaw of plate tectonics snaps together. They fit when you assemble their drift lines and collision timings. Even the speed-ups, stalls and bends in mountain belts show up in the magnetic record as changes in how fast those paleopoles move. This iron diary is practical too. Archaeomagnetism dates hearths and kilns by reading the field direction recorded when the clay last cooled. Volcanic hazard teams map young lava flows' magnetization to know which vents made which layers. And the core's behavior, jerks, wobbles, long quiet spells, appears in stacked records from lavas and sediments worldwide, letting us model the metal ocean that powers the field. All of this relies on humble grains, a few micrometers wide, that quietly copy the sky each time they cool or settle. The element that came from dead stars ended up as the ink our planet uses to sketch its moving surface and its restless magnetic shield, so a hand sample on a lab spinner can tell you where a continent once was and which way a compass pointed 100 million years ago. The same iron nucleus that ends fusion in stars shows up on Earth wearing many different outfits, and each outfit tells a story about the place it formed. Change how much oxygen is around, change temperature or water, and iron flips between Fe2+, more reduced, and Fe3+, more oxidized. Building different minerals with different looks and behaviors, hematite, Fe2O3, is iron in its rusted state. It's usually steel grey or red, and it gives a red streak when scratched on unglazed tile. That streak is why red beds and old soils glow. Tiny hematite grains have been ground for millennia into red pigments. Goethite, an iron oxyhydroxide, makes yellow-brown ochres and forms in damp, oxygen-rich weathering. See it in rusty crusts and mottled clays. Magnetite, Fe3O4, mixes Fe2+ and Fe3+, and is strongly magnetic. A hand magnet will happily find it in dark volcanic sands and layered iron ores. That built-in magnetism lets lava and ash record the direction of Earth's field as they cool, turning outcrops into paleomagnetic tape, our striped seafloor story from Act 15. Siderite, iron carbonate, forms in low oxygen, CO, too rich waters and bogs. Find it, and you're likely looking at an environment that kept oxygen at bay. Pyrite, FeS2, the famous fool's gold, grows brassy cubes in places starved of oxygen, like seafloor mud or coal seams. Its sparkle tells you chemistry was reducing, and when those rocks later meet air and water, pyrite can make acid mine drainage. Orange streams with iron flocks are the consequence. Flip the setting and iron builds ilmenite, FeTiO3, in hot magmas, or chlorite and biotite, iron-bearing micas in metamorphic rocks. Each mineral is a thermometer and barometer in disguise, hinting at the heat and pressure the rock endured. Even color is a quiet lab report. Deep reds and browns mean oxidized iron, grays and greens often mean reduced iron, and jet black magnetite signals hotter, less watery paths. On Mars, hematite blueberries and red dust say water once met iron and time did the rest. In industry, the iron oxide pair, hematite and magnetite, are the heavy lifters. They're dense, magnetic, and concentrate into mineral layers by settling in magma chambers, by chemical precipitation in ancient seas, or by being left behind as other elements wash away. Geologists carry 3 pocket tests for iron at outcrops. A magnet, does it jump? A streak plate, red, black, or none? And weak acid, does siderite fizz? Museums show the beauty, radiating hematite roses, perfect pyrite cubes, glinting bands of magnetite and quartz, but the quiet power is the environmental memory baked into each crystal. Swap electrons between iron 2+ and iron 3+, change the partners, oxygen, sulfur, carbon, water, and iron writes down whether the world around it was hot or cold, wet or dry, breathless or airy. That's the pattern of this whole series. A single element, born in supernovas, becomes a language. Learn the few common words: rust, magnet, fool's gold, red streak, and you can read rocks like a diary, from a marsh that kept oxygen out to a lava lake that cooled under a clear, dry sky. Stand on a windy coast and watch a tan haze blow in from a desert, and you are watching a global delivery service at work. Grains too small to see carrying a whisper of iron from dry land to the open ocean, where that iron can flip a biological switch. Far from coasts, the surface ocean often has plenty of nitrogen and phosphorus, but barely any dissolved iron, because iron rusts, clings to particles, and sinks in those high-nutrient, low-chlorophyll regions. A pinch of iron is all that's missing for microscopic plants, phytoplankton, to bloom. When windstorms loft dust, or volcanoes scatter ash, and it falls on those waters, chlorophyll rises, the sea turns greener, and tiny cells turn CO2 into organic carbon. Some of that carbon is eaten and recycled near the surface. Some sinks as marine snow, dead cells and grazers' pellets, carrying carbon into the deep. For years to centuries and over ice age cycles, the planet seems to have used this lever. Colder, drier climates made dustier air. Dust delivered more iron. Plankton pulled a bit more CO2 from the sky. The air cooled a little more. A small, slow feedback, not a master switch, but real. Scientists tested the idea by sprinkling dissolved iron across small patches of the Southern Ocean and North Pacific and watching satellite color and ship instruments. Blooms popped, gases shifted, and sinking particles increased. The lesson was twofold. First, iron truly is the missing micronutrient over huge ocean areas, so the planet's carbon pump is sensitive to a trace metal born in stars and blown as dust. Second, nature's web is tangled. Blooms changed food webs, altered other gases like nitrous oxide and dimethyl sulfide, and much of the carbon was recycled before sinking. That's why large-scale geoengineering by iron seeding is controversial. Ocean chemistry, ecosystems, and regional climates are not knobs you turn without side effects. Still, the quiet point stands. Saharan dust crossing the Atlantic, Australian dust streaking the Southern Ocean, ash from an Aleutian volcano. Their iron content helps set how busy the ocean's surface factories are, which nudges how much CO2 the air keeps. Clouds feel this too. More plankton can mean more airborne sulfur compounds that seed cloud droplets, brightening clouds and reflecting sunlight. None of these effects is dramatic like a storm. They are the planet's sleep mode. Tiny adjustments made by countless cells using a metal that cannot be made on Earth at all. In the long chain from supernova to skillet, this is one of iron's softest roles. A trace in the wind that feeds the sea, that feeds the pump, that quietly leans the climate a little one way or the other. If iron on Earth came from dying stars, there should be moments when the sky actually dusted us with fresh star ash, and it turns out the planet keeps a quiet record of those visits in a rare flavor of iron called iron 60. Normal iron in your pan is iron 56, and it is stable. Iron 60 is a heavier cousin with 2 extra neutrons that slowly falls apart over a few million years. That short lifetime means any iron 60 left from the birth of Earth vanished long ago. So if we find iron 60 near the surface today, it had to arrive recently on the geologic clock. Researchers looked where the planet slowly builds time capsules. On the deep sea floor, metal-rich coatings grow on rocks and nodules a hair's breadth per million years. In those layers, teams measured tiny spikes of iron 60, peaking a few million years ago and again a little earlier. Antarctic snow and ocean sediments show the same whisper. Even lunar soil brought back by astronauts holds a faint signal. The story those spikes tell is simple and wild. A few nearby stars in our part of the galaxy reached the end of their lives, exploded, and sent out shells of gas and dust. Some of that dust contained iron made in the blast, and fresh iron 60. As the shockwaves moved through the thin gas between stars, our solar system drifted through the debris, and a slow drizzle of grains fell into the sun's wind and then down onto Earth and the Moon. The amounts are tiny, far below anything dangerous, but enough for modern instruments to count. The timing lines up with a guess about our local space. The sun sits inside a bubble of hot, low-density gas that may have been carved by a chain of supernovas from a moving group of stars that passed nearby in the recent past. The iron 60 in deep sea layers could be the soot from that carving. This is not just a neat detective trick. Iron 60 layers let us place real dates on nearby blasts, test how dust drifts through space, and check how the solar system's shield works against slow rain from outside. The signals also act as a cross-check for other clues, like cosmic ray changes in ice cores and oddities in fossil records, though those links are still debated and should be handled with care. What is not debated is the core message. Far away and long ago is not the whole story. On million-year scales, stars in our neighborhood live, die and brush our world with their ashes. Some of that ash is iron, the same element in your blood and bridges, arriving grain by grain. The galaxy is not only the place that made your iron, it is still, very gently, delivering it. Long before people floated needles on water, life had already learned how to use iron to sense direction. In ponds and estuaries, single-celled magnetotactic bacteria grow chains of magnetite crystals inside little membranes called magnetosomes. Each chain is a microscopic bar magnet. It lines the cell up with Earth's magnetic field so the bacterium can swim to just the right depth, where oxygen is low but not zero. That's iron doing navigation at the smallest scale. Iron 3 oxygen, 4 grown like beads on a string, turning a cell into a compass. Bigger creatures seem to borrow the trick, though the story is more complicated. Homing pigeons, migratory songbirds, sea turtles, salmon, even some insects behave as if they read the planet's field. Give a pigeon a brief magnetic pulse, and it flies off on a wrong heading for a while. Expose a night-migrating bird to weak radio frequency noise, and it loses its compass until the noise stops. Raise hatchling turtles under shifted magnetic fields, and they swim as if the coastline had moved. These are calm, repeatable signs that animals can feel magnetic direction. Where is the sensor? There are two leading ideas, and they may both be true in different parts of the body. One uses iron directly, tiny particles of magnetite, or the rarer graphite, anchored in tissue tug on springy proteins when the field turns, opening or closing ion channels and sending a nerve signal. Some studies point to iron-rich endings along the trigeminal nerve in the faces of birds and fish as candidates. Another idea is light-dependent and lives in the eyes. A photoreceptor protein called cryptochrome can form short-lived paired molecules whose spins are nudged by the magnetic field. That quantum nudge may bias chemical outcomes, letting a bird see a faint rotating pattern overlaid on its normal vision when blue light is present. Both pathways have experimental support. Both have puzzles iron particle sensors found in bird beaks turned out, in some papers, to be immune cells rather than nerves. Cryptochrome effects are delicate and need specific light, yet many animals orient in darkness. The honest state of play is this. Magnetite-based compasses are rock solid in bacteria and strongly suspected in some animals. Cryptochrome-based compasses are supported by clever lab tests and tracking experiments in birds. Different species may mix and match. Either way, iron sits at the heart of at least one strategy. Magnetite is just iron and oxygen arranged so that unpaired electron spins add up, making a permanent tiny magnet. Grow it in uniform sizes and chain it, and you have a built-in needle. That's a beautiful echo of the element's cosmic story. Iron born in dying stars ends up guiding a bacterium to its preferred mud, a turtle across an ocean, and a pigeon back to its coop. And because the magnetic field comes from Earth's own iron core churning far below, the loop closes even tighter. Iron in the planet whispering to iron in living tissue, a quiet conversation running from the center of the Earth to the edge of a wing. Iron is generous, but the way we free it from rock has a heavy cost. Most iron ore at Earth's surface is iron oxide, iron already holding hands with oxygen, and for 2 centuries we have broken that bond with hot carbon in blast furnaces. Carbon pulls the oxygen off the iron and leaves as carbon dioxide. Scales and chimneys make it look old-timey, but the chemistry is modern and blunt. Big heat, big oxygen removal, big CO2. Steelmaking is a few % of global emissions all by itself because we move so much rock and run so many furnaces day and night. The good news is, the recipe can change without magic. If the job is, Take oxygen away from iron. We don't have to use carbon. We can use hydrogen. In direct reduction plants, pellets of iron ore flow through a tall, hot shaft, while a stream of hydrogen meets the ore and quietly steals its oxygen. Instead of CO2, the exhaust is mostly water vapor. The output is solid, spongy iron called DRI that can be melted in an electric arc furnace and turned into steel. Swap the furnace's power to renewable electricity, and you've cut most of the carbon out of the process. There are other practical steps. Melt scrap steel with electric arcs, and you avoid most ore reduction entirely. Use natural gas in DRI as a stepping stone while green hydrogen supply grows. Capture the CO2 from traditional furnaces where that makes sense. Push more recycling so every car body and bridge girder lives 2 or 3 lives. New approaches are maturing too. Some groups are testing molten oxide electrolysis, where you dunk electrodes into a bath of melted rock and use electricity to pull oxygen off iron directly, producing oxygen at one side and liquid iron at the other. Others are piloting hydrogen made from water by electrolysis, fed with wind and sun, rather than hydrogen from fossil fuels. None of this erases the basic needs. You still mine, move, heat and shape huge masses of material. You still need ore pure enough for these routes, and enough clean electricity to run them. You still need logistics for hydrogen that are safe and affordable. But the physics is on our side. Iron wants to let go of oxygen if you offer it the right partner and enough thermal help. The arc furnace is already a mature way to melt metal with electrons instead of flames. Hydrogen already leaves as harmless water if it does the pulling. The near future of this star metal is not a fantasy of levitating cities. It is the steady swap of fuels, furnaces, and feedstocks. So the rails, towers, and ships we still need don't come with an invisible heat bill. It's fitting, really. The element that ended the fire in dying stars gave us the tools to build a world. Now we get to keep using it while turning the flame down. If iron ends the fire inside dying stars, you can ask a calm, late-night question. What happens to iron when the universe itself grows old? The short answer is that iron tends to be a resting place. It sits near the top of the binding energy hill, which is a simple way of saying nuclei. Near iron are the most tightly glued together per particle. That's why fusion climbs toward iron to make energy and then stops. After our era of bright stars, most starlight fades as fuel runs out. White dwarfs, hot, city-sized embers, cool into dark black dwarfs. Neutron stars and black holes keep orbiting like silent anchors. Out in space, rust-colored dust stays dust, drifting between cold, red stars. In some cataclysms, iron won't rest. When 2 neutron stars merge, pieces of ultra-dense matter spray out and build elements heavier than iron in a rapid neutron storm. When matter falls onto a neutron star or into a black hole, iron can be crushed or swallowed. But without those rare fireworks, iron is a finish line for normal nuclear cooking. Push the clock absurdly farther, numbers so large they don't feel real, and a few speculative paths appear. If protons are perfectly stable, we don't know, then over unimaginable spans, tiny quantum tunneling reactions could, in theory, let the nuclei inside ultra-cold black dwarfs shuffle toward even tighter arrangements. Some physicists once coined the term iron stars for an ultimate state where matter drifts toward iron-rich lumps because iron is so tightly bound. If, on the other hand, protons slowly decay, some theories allow it, then even iron would not last forever. Its pieces would crumble into lighter particles and the periodic table would unwind. Both pictures are working ideas, not settled facts, and either way the timeline is so long that words like trillion hardly start the count. Bring the thought back to scales we can feel, and the theme stays simple. Iron is a stable landing pad in a universe that runs downhill from high energy to low. That's why supernovas leave so much of it, why Type Ia explosions shine on nickel that becomes iron, why asteroids carry iron cores, why Earth sorted iron to its center and kept a little in rocks, and why your body borrows it to shuttle oxygen. In the far future, when bright blue stars are gone and only dim coals glow, iron will still be there in meteorites, frozen into black ice, in the quiet hearts of dead worlds, in dust that never found a new sun. The same nucleus that sits in your red cells tonight looks like a final chapter. The cosmos writes toward, not because the universe loves iron, but because its rules make iron the comfortable end of the road for ordinary matter. We can now tell the whole story in one breath. Iron did not begin here. It was built in the last frantic stages inside massive stars and in the bright depths of white dwarfs, piled up as nickel that cooled into iron, then thrown into space by shockwaves and neutrino winds. That ash drifted for ages, stuck to dust, and settled into dark clouds. Our sun lit inside one of those clouds, and the leftovers formed a hot disk where rock and metal survived near the center. In that mill, iron was a stubborn solid that helped dust become pebbles. Pebbles become worlds. Some small bodies melted and made little iron cores. Some broke and sent iron meteorites wandering. Earth grew from the same mix, heated and sorted itself. Metal sank to make a core. Rock floated to make a mantle and crust. The liquid outer core began to roll, and with it, a magnetic field rose that still shields our air and guides auroras. A thin share of iron stayed at the surface and joined water and oxygen in a slow dance of rust and red soils and banded iron layers that record the first breaths of life. Life chose iron because its electrons trade hands easily. It sits in hemes and clusters, carries oxygen in your blood, and passes charge in your cells while your body hides and guards it. We proved the sky connection with our own eyes and instruments. Iron lines in starlight, iron glowing in supernova wreckage, iron 60 sprinkled in sea crusts and lunar soil, fingerprints of meteoritic nickel and cobalt in old blades, metal cores exposed in broken asteroids. We learned to reshape star metal into steels, magnets, rails, bridges, and ships, and we are learning to make it cleanly with hydrogen and electrons, so the gift does not smoke the sky. Look outward, and the pattern repeats on other worlds. Mars painted red, Mercury built on a giant heart, hot giants where iron may reign, rocky exoplanets heavy or light with metal. Look far ahead, and iron sits where the universe likes to rest, a tightly bound endpoint that lingers after brighter fires fade. The quiet truth beneath every step is simple. One element, made long before us, now runs our compasses, guards our planet, builds our cities, colors our deserts, feeds our seas, and moves with every breath you take. If you hold a small meteorite or a stainless spoon, or press a finger to your wrist, you are touching the same nucleus at 3 scales: star, world, and body. That is a good place to stop for tonight. Thank you for listening, and good night.